bounded sequences. So yeah, let's go over bounded sequences and go over definition 5, which states a sequence AN is bounded above if there is a number such that the sequence, all the terms AN are less than or equal to M, and this is for all positive integers. So N is greater than 1, greater than or equal to 1. Yeah, so that is a definition of bounded above, and it's called bounded below if there is a number M such that M is less than or equal to every single term of the sequence AN for all positive integers, or all N is greater than 1, greater than or equal to 1. And yeah, just denote them by lowercase m for the bounded below and uppercase M or capital M for the bounded above. And then finally in the definition it says, if it is bounded above and below, then the sequence AN is a bounded sequence. So yes, very, very interesting. So yes, if it's bounded both, then it's strictly just called bounded. And that's the definition. Put a line over there. So for instance, the sequence AN equals to N is bounded below because AN is well greater than 0 when N is equal to 1. That's the lowest one it could be, 1, then it goes 2, 3, 4, etc. But it's not bounded above because you can always get a bigger and bigger number because N goes to infinity. And the sequence AN equals to N divided by N plus 1 is bounded below and above, so it's bounded so it's a bounded sequence since AN is greater than 0 and less than 1. Yeah, so if you recall, I covered this particular sequence several times in this video earlier, and yeah, it's a sequence that this one, as you get bigger and bigger, as N goes to infinity, you're going to have infinity over infinity. They approach 1 and it goes to infinity, and also the lowest number. Yeah, the lowest number here, you could see that if you put 1 in there, 1 divided by 1 plus 1 is 1 over 2. So the lowest could be is actually 1 over 2. Yeah, so it is. Yeah, so it is bounded because it's greater than 0 and less than 1, or greater than or equal to 1/2. But anyways, for all N. Yeah, so now going further, we know that not every bounded sequence is convergent. So just because it's bounded does not mean that it has to be convergent, or meaning there's a limit. And an instance is shown below, which I covered earlier. So remember, AN equals to -1 to the power of N. This satisfies being bounded because it is AN, it's less than or equal to 1. Remember, it just alternates between -1 and 1, and it's greater than or equal to -1, but it is divergent. It is divergent, and this is as in example 6. Yeah, from example 6, which I covered again, which it alternates from -1 to 1, so never actually approaches a limit. And now, going further, we also know that not every monotonic, again, remember that's increasing or decreasing, so not every monotonic sequence is convergent. And yeah, for example, AN equals N, well, this approaches infinity, even though it is increasing. It's always getting bigger and bigger, 1, 2, 3, 4, but it's not convergent, so there's no limit. It goes to infinity. But if a sequence is both bounded and monotonic, then it must be convergent. And this fact is proved as the following theorem, as I'll go into it. But intuitively, you can understand why it is true by looking at the figure below, and it's yeah, pretty straightforward why it should be, because it's always increasing or decreasing, and there's a limit. I mean, and it's bounded, so bounded below and above. So it has to be, yeah, approaching a limit that's going to be less than whatever it's bounded by. So, for example, yeah, let's just graph this out. Let's say there's AN on this chart, and let's say it is bounded below, so it's bounded below, bounded above, so bounded above, so AN is always, every single term is going to be less than or equal to M, so capital M there. So let's say it's bounded like that, so it can't go above this one, but the sequence is always going to be increasing. Yeah, so it's monotonic, so let's assume it's increasing, so it's going up like this, it's going up. But eventually, because there's a limit, it can't get anywhere near there, so there has to be a limit like this. L, where L could equal M, if it has to. But it just can't be bigger than that. So then it has to converge somewhere. So it's bounded by L and M, and L could be M. It depends. And again, this is just increasing. And it has a limit, because it's bounded, so i.e. monotonic. Monotonic. So if it's increasing or decreasing, it's monotonic, or one way moving. Yeah, so yes, this was a very good intuitive illustration. So basically, if an is increasing and an is less than or equal to m for all n, so it's bounded above, then the terms are forced to crowd together and approach some number L, which could even equal to m. So it's always increasing, but it's still approaching the limit. And the proof of the following theorem is based on the completeness axiom. Yeah, just to prove it in more mathematical rigor. So it's the completeness axiom for the set R of all of real numbers, which says that if S is a non-empty set of real numbers that has an upper bound, yeah, so that X is going to be less than or equal to M for all X in S, then S has a least upper bound B, which means that B is an upper bound for S. But if M is any other upper bound, then B is less than or equal to M. So yes, that's a lot of mathematical mumbo jumbo. I'll illustrate this in a bit more detail soon, just to make some sense out of this. So the completeness axiom is an expression of the fact that there is no gap or hole in the real number line. Yeah, so for example, let's say we have a number line like this. There's X, there's 0, example, and then let's say we have a set R of real numbers, or all real numbers. Let's just say that S is everything. It goes on and on. R is everything. So this is a set of all real numbers. Like that, it goes everywhere. And then which says S is a non-empty set of real numbers that has an upper bound M. Yeah, so let's say S, yeah, so it has an upper bound M. So what we'll do is, will be a set of real numbers from all the way to the left. And then moving all the way to, but instead of all real numbers, like this, we get all the way up to here, which is M. And this is S. And I'll draw S like this. It indicates it's a set, so it stops right across over there. Yeah, so that is bounded above, but it's pretty much similar to this one, where that's L is going to be considered, could be considered as a least upper bound. That's the upper bound there. So what we have is, then there is then it has a least upper bound B. So let's say it has value B like this. Yeah, so any number you pick B like this, it's going to be less than M. Yeah, if this is the least upper bound, so if it's if we say it's less than this one, but if M is anything other than B, then it's obviously going to be, well, between this. This is basically all it's saying, that B is always going to be less than or equal to M. Yeah, so essentially this is the same thing as this one. So this B could be viewed as L, like that. So that is the upper bound or the limit. But if an upper bound exists, that's then it's, if another upper bound exists that is not the limit, then it's obviously going to be less than the upper bound there. So that's pretty much what it's saying. Yeah, so essentially this stems from what's called no gap or hole, and that means that every number can have infinitely amount of numbers past the decimal place, hence a least upper bound B can always be found that is B less than or equal to M. So yes, just go over just a quick mainstream view of this completeness axiom. Is very interesting. Again, this is more rigorous mathematics. So completeness of the real number. Intuitively, completeness implies that there are not any gaps in Dedekind's terminology or missing points in the real number line. This contrasts with the rational numbers whose corresponding number line has a gap at each irrational value. In the decimal number system, completeness is equivalent to the statement that any infinite string of decimal digits is actually a decimal representation for some real number. Yeah, so depending on the construction of the real numbers used, completeness may take the form of an axiom, the completeness axiom, which is stated above there, or maybe a theorem proven from the construction. There are many equivalent forms of completeness, the most prominent being Dedekind's completeness and Cauchy completeness. And completeness is a metric space. Very, very interesting stuff. Yeah, I might go over that later, but I'll just stick with the axiom for now. Yeah, so essentially it's saying, mathematically, make an axiom saying that a limit exists if there's an upper bound and the function is always increasing. Or in decimal places, if you keep adding numbers to the decimal, the number is increasing. But it's still approaching a limit. And that limit could be M, but it's going to be less than or equal to whatever it is bounded by. So anyways, let's go further. So now that all this was for the monotonic sequence theorem, which is stated above, but now write it as a theorem. Every bounded monotonic sequence is convergent. So every bounded, so has an upper and lower bound, upper or lower bound, and it's monotonic or increasing, or increasing or decreasing, then the sequence converges to a limit, or is convergent. And here is the proof. So suppose AN is an increasing, hence monotonic, and bounded sequence. Yeah, so if it's increasing, hence monotonic and bounded, that means, well, since an, since an is bounded, so it's bounded and it's increasing, hence it has an upper bound. The set, so put the set S, make it all the numbers inside an where n is greater than or equal to 1, then this has an upper bound. Yeah, so this has an upper bound. An upper bound because because it is bounded. So it's bounded and it's always increasing. Yeah, so by the completeness axiom, it has a least upper bound. We'll call that L. Again, BL is, as I said, is essentially the same thing in both the illustrations above. So given that epsilon, so if you're given a number, epsilon greater than 0, then L minus E is not an upper bound for S. Yeah, since L is the least upper bound, and L minus E, or L minus epsilon is less than the least upper bound. It's because we're subtracting 1 from it. So therefore, if we have this number number epsilon, so that's what we have is A, and we'll have a capital N, is greater than L minus epsilon for some integer n. Capital N, like that, because there's at least upper bound exists. And this is this number is less than. So if we're given there's a number less than it where the term is less than L, then we have to have some integer capital N where a n is greater than this this value right there, L minus this epsilon. But the sequence is increasing, so because it's monotonic and we're assuming it's increasing right here. So a n is greater than or equal to a capital N for every n is greater than n. So then, so if we have n if n is greater than capital N, then it's always going to be bigger than this value there. So thus, if n is greater than, if n is greater than capital N, we have, an is greater than or equal to, a capital N, where this one already we know is going to be, greater than the least upper bound minus this epsilon. So that's what we have, is just take these two terms. This one is going to be now an is greater than L minus epsilon. And now what I'll do is just rearrange this, write epsilon on its own. So move this over to this side, move this over to this side. So then what we end up getting is we get epsilon is greater than L minus an. And now this value right here, this has to be greater than or equal to 0, and this as well, since we know that this is the least upper bound. So that says, so since an is going to be less than or equal to L, so it can't be anywhere any larger than it, so it's always going to be a positive number. Put that bracket like that. And now I'll just flip this around, rearrange this, or writing it as 0 is less than or equal to L minus an, and less than epsilon. Just write it this format, so it's greater, make the 0 on the left side. Yeah, so thus what we have is, thus the absolute value, this is going to be greater than 0, or we could write this as the absolute value of L minus an is going to be less than epsilon, and this is whenever n is greater than capital N. Again, as above here. So in other words, we have the limit. This is the definition of the limit. And we have limit now as n approaches infinity as an equals to L. So that's just a definition of the limit. So yes, very interesting, just using the mathematical rigor of the axiom theorem to apply it and show that it's essentially the same thing as the limit there. So it proves that there's a limit for a monotonic and bounded sequence. Every bounded monotonic sequence is convergent, so it converges to a limit. So a similar proof using the greatest lower bound instead of the upper bound for the other side works if an is decreasing. And the proof of the above theorem shows that a sequence that is increasing and bounded above is convergent Likewise, a decreasing sequence that is bounded below is convergent, where it has a greatest lower bound as opposed to the least upper bound. And yeah, so that's going to be one to the left of the number line. And yeah, this fact is used many times in dealing with infinite series.